In this lesson, we'll be solving equations that have radicals or square roots in them. So let's just start with an example. If we want to solve example 1a, square root of x minus 3 plus 4 equals 7, we have to isolate the radical, and then we can square both sides. In this case, isolate the radical means subtract 4 from both sides. That leaves me with root x minus 3 equals 3. Then I can square both sides. Squaring a square root, well, those are inverse operations, and that actually gets rid of the square root. So on the left-hand side, I have an x minus 3, and on the right-hand side, I have 9. Finally, this is an equation we can solve. We just add 3 to both sides, and we end up with x equals 12. Now, when solving equations with radicals, you do actually have to check your answers. As we'll see in the next couple examples, it's possible to get false or extraneous solutions. To check my answer, I just take the 12 and I plug it back in for x into that equation. I end up with a square root of 9 plus 4 equals 7. That is a true statement. 3 plus 4 is 7, so my answer is x equals 12. Now let's look at a slightly more complicated example. We're going to do the same thing though. The radical is by itself, so I'm going to start by squaring both sides. When I square the left-hand side, that gets rid of the radical, and I just have 6x plus 7. I have to be a little bit careful when I square the right-hand side. I want to make sure I use FOIL on that. My first would be x squared. My outer and my inners are both 2x. Together, that's 4x. And last term is 4. Now, in this case, I actually have a quadratic equation, something with an x squared. So if I want to solve this equation, I have to set one side to 0. And with quadratics, it's easiest if the x squared term is positive. So I'm going to set the left-hand side to 0. That means subtracting the 6x, subtracting the 7, and combining like terms. Now I'm going to see if I can factor. Product of negative 3, sum of negative 2. Minus 3 and plus 1 work. They have a product of negative 3 and a sum of negative 2. So I have two possible answers, x equals 3 and x equals negative 1. Now I do have to check both of these answers. It's possible both work. It's possible neither works, and it's possible that only one works. So I start by plugging 3 in for x into the original equation, and I go through the arithmetic. On the left, I end up getting a square root of 25, and on the right, I get 5, and that's a true statement, so 3 works. And when I plug in negative 1, it turns out I also get a true statement, root 1 equals 1, so in this case, both solutions work. Now again, that's not always going to be the case, as we'll see in the next example. Sometimes one or both of your solutions may not work. So let's try one more example with a square root. We isolate the radical. That means subtract 10 from both sides. I square both sides. Squaring the radical, those are inverse operations. That gets rid of it. And this is an equation I can solve. This one's linear, so I just have to get the x by itself. And x equals negative 1. We check our solution by plugging negative 1 in for x. And this time I end up getting, negative 2 plus 3 is 1. So I get square root of 1 plus 10 on the left. That is 11, which is not the same as 9. And so this equation has no solution. Finally, this technique also works for other types of roots. In example D, I have a cube root. If I want to get rid of a cube root, I cube both sides. That gets rid of the radical. 4 cubed would be 4 times 4 times 4. That is 64. Add the 2, x is 66. With cube roots, you actually don't have to check your answer. It's not wrong if you do, but you don't have that same issue of getting these false extraneous solutions. In this lesson, we're going to look at one application of square roots, and that would be the Pythagorean formula, and a variation of that called the distance formula. The Pythagorean formula applies when you have right triangles, triangles with 90-degree angles. The sides of those triangles are related according to the formula a squared plus b squared equals c squared, where c is the length of the hypotenuse, or that longest side in the triangle. One application of the Pythagorean formula is something called the distance formula, which lets us find the distance between 2 points in the coordinate system. So we have an x1, y1, an x2, y2, and we want to figure out what is the distance between those points. Well, we already know how to compute the rise and the run, and if we do that, that turns this into a right triangle problem. The rise is our change in y, the run is our change in x, so using the Pythagorean formula, rise squared plus run squared equals distance squared. Or change in y squared plus change in x squared equals distance squared. If you want to solve this for d, you can by taking the square root of both sides, and that big complicated formula is what's known as the distance formula. Now, honestly, rather than memorizing that formula in blue, that distance formula, I think most people find it easiest to just draw a right triangle and use the Pythagorean formula, the formula in green. I want to find the distance between the point -2, 5, so x is -2, y is 5, and the point 4, 2, x is 4, y is 2. I'm going to compute the rise and the run, and then turn this into a right triangle problem. The rise would be the change in y, 5 minus 2, which is 3. Or you can just count the boxes from y equals 2 to y equals 5 is 3 units. The run, the change in x, would be -6. Although it turns out with these problems, because we're talking about distances, the order of the subtraction doesn't matter. This is a right triangle with a height of 3 and a base of 6. So using the Pythagorean formula, 6 squared plus 3 squared is distance squared. 36 plus 9 is 45. So our distance is square root of 45. And we can simplify that because 45 is 9 times 5. Root 9 turns into a 3. And so the distance between those 2 points would be 3 root 5. All right, that's it for this lesson. I know there's a lot of material in here. Please don't hesitate to contact me if you have any questions on this content.